Welcome to EE252 Electronic Devices and Circuits. We have been talking about modes of operation of the BJT. Last time we talked about the semiconductor, the basics of the BJT, and there we identified that when the when there are two junctions in the BJT, and when one of these is in the forward bias direction and the other one is in the reverse bias direction, the transistor behaves in a different way than what we expect. We discussed about it last time, and we said we can characterize this by an external energy model, which is characterized by a constant current ratio between the current in the collector and current in the gate. So, to capture the external energy model, the equation that we came up with was beta equals IC over IB. Right? And then we went on to talk about the modes of operation of BJT, and there again we emphasized that depending on the number of forward bias junctions in the transistor, that there are three different possible states. Okay? And when there was only when there were no junctions forward bias, right? Both the diodes are considered switched off, so reverse bias. So therefore, no accessible current flows in this. So therefore, we call this a cutoff mode. No current in any of the branches. IB, IC, and IE are all almost zero. Right? The second case, when only one junction is forward biased and the other one is reverse biased, we call this active linear mode. This is the one that we use for amplification for purposes, and this is what has been characterized by this external energy model, where the relationship beta equals IC over IP. Right? And then we also talked about the case where you have both the junctions forward biased. We call this the saturation mode, and we mentioned that saturation typically depends on the external circuit, but not on the transistor itself. So saturation is a property of the circuit, the power supply and the external resistors, the load. Right? So therefore, this is what we are going to start talking about today. Right. So let me talk about the cutoff mode first. Let's go into a little bit more detail here. Cutoff mode. Cutoff mode. In this, what happens is we have the diode, not collector, base, and the emitter as such. It is an transistor. So if you make both these diodes, so this is what this looks like. This. Okay? This is what it looks like. So if you make both these junctions reverse bias, that means this has to be reverse bias as well as this. Like that. Right? So both are reverse bias. like this. Okay, so base emitter junction voltage is less than the forward voltage of this junction. So for silicon diodes, this value is roughly about 0.7. So therefore, base emitter voltage, this voltage is less than 0.7. It could be, as indicated, it is negative. It doesn't even have to be negative. Anything below 0.7, it will be reverse bias. Okay. Similarly, the DC is also less than the forward. For the BC junction. Now remember, I am putting that EE and BC subscripts also to indicate that they can be different. In fact, they are different because they are the collector and emitter are not equally so. Okay, so they are different. Okay. So under this condition, no significant current flows. Okay. Right. So none of the currents IB, IC, or IE are zero. So I can draw this in transistor configuration like the base and the plate. So this is basically, there's nothing much to look at this. Everything is at a standstill. The second one, and the most important one actually, is the active linear mode. In this case, one of the junctions are forward biased and the other is reverse bias. Now there are two junctions, so therefore you can select either BE junction to be forward bias or BC junction to be forward bias. However, remember this transistor BC and BE are not the same because B and C are not equally doped. So therefore, in designing the transistor, it is designed assuming that BE will be in the forward bias and BC will be in the reverse bias direction. If you have it the other way around, in other words, BC in forward bias and BE in reverse bias, it will work, but it will not be efficient. Okay? So therefore, what is expected is, in order to obtain the expected behavior, what we want is base emitter junction to be forward bias and base collector junction to be reverse bias, not the other way around. Okay? So when one forward bias junction, typically base emitter junction, and one reverse junction, typically base collector junction. Okay? Note that collector and emitter are not doped by the same amount. Therefore, they behave differently. Though it is not captured.
Excuse me, sir. Can you hear me?
Yes.
Sir, your voice is not bit clear. We can
Okay.
hear you, but it's not clear.
Okay, hold on. Yeah, I will try to use it.
Thank you, sir.
For the microphone. Thank you for letting me know. And you guys can't see my screen either, or you can see my screen, right?
Yes, sir. We can see your screen, but your voice is not clear.
All right, I'll change my microphone. How about now? Is it better?
Ah, yes, it's a go. Yeah, okay, go on, sir.
Much
Thank
better,
you.
right? Is it better?
Yeah, sir. Now it's clear. Yes.
Okay, thank you very much. Thanks for pointing it out. Okay, all right. So therefore, the behavior, so they behave differently, so it is not captured by the junction model. So though it is not clear from the junction model. Okay. So the forward bias base emitter junction can be modeled as a using the Eber small model, because it's just a forward bias junction. So it's a diode, right? It behaves like a diode. So what is that? The current through emitter is equal to the reverse saturation current, Vs, to the VBE base emitter, that is the voltage, divided by N times Vt minus IES, right? So this is the Eber small model. Basically, what it looks like is something like this. So this is the voltage, and this is the current. So it let me call this IB. Okay, something like this. So this is the whole thing. For base emitter voltage greater than about 0.7, this does not change much. So therefore, we can approximate this base emitter voltage. So this the relationship between IB and VBE can be reduced to VB approximately equal to 0.7. In other words, the IB does not depend on VBE does not depend on IB, kind of a relationship. So that is only for this region, though. Okay, you have to remember that, because it doesn't. It's basically that region. Okay, this is for silicon diodes, volts, millivolts. Oh yeah, 0.1 volts. So what we had was something like this. The collector, emitter, so the current through this is IC. This is the collector, the base emitter, and this is IE. This is IB. Okay. So if you look at the diode model, it looks something like this. So in here, what we make is base emitter junction. This junction forward bias. So this voltage is in this direction, and hello, you guys can still hear me? Hello.
Yes, sir.
Yes, sir.
Hello.
Yes, sir, we can hear you.
Hello, do you guys hear me?
Yes, sir, we can hear you.
Hello. Hello. Can someone please stop? I don't know.
Hello, sir. We
can-
can hear you.
Hello. Some weird reason I can't hear you. Let's speak. Hello.
Hello, sir. We can
Okay.
hear you, sir.
Okay, that's good. That was my audio system. That was okay. So let's continue. So this way, VBE is positive, but VBC is negative. So therefore, this is still like that, the negative reverse bias, but this is forward bias, something like this. Okay, so that's basically the arrangement that you should have. So under such conditions, we remember that we said we can use the external energy model to characterize the relationship between IC and IB. What is IC and IB? So we have the transistor, right? So we have the base, collector, emitter. This is VBE. This is VCE. Sorry, VBC, IC, IB, and IB. Okay. So according to the external energy model, beta is equal to IC over IB. Okay. Now for if you have base emitter junction forward biased and base collector junction reverse bias, like in the way it is designed to be used, this value is about 100. It's a pretty big value. There's a large current gain. This is called the current gain, and this value is pretty large. In order to get this, base emitter voltage should be VBE should be greater than V forward bias of the base emitter junction. So it is typically about 0.7 volts because it doesn't change much. And VBC is less than V forward bias of the base collector junction. So this is a negative level, right? So therefore, what you will have is something like this. Now, however, it is also possible, this is the way it is, if it is as intended, right? So if this is the case, beta is about 100, IC over IB, okay? Beta, which is equal to IC over IB, is in the range of 100, a pretty big value. However, it is also possible to connect it in the opposite method, like, reverse mode. We call this the reverse mode, right? So this is the correct mode, but if we connect it the other way around, in other words, the base emitter junction reverse bias and base collector forward bias. So this is called the reverse mode. Reverse mode where VBC is actually greater than VF of BC and VBE is less than V forward. Okay, so this is if you connect it something like this. Okay, so So this is base emitter collector, where this one is like that, like this. Okay. So in which case the currents are IE, IC, and IB. VBC is forward bias, but VBE is like that. It's a negative. Okay. So this is like, let's say, for example, if this is 0 volts, this is 1 volts, and this is 10 volts, something like this. Under such situations, this is not what is expected. In such situations, this IC over IB beta is not as big. So it's called beta reverse. This is about 5. Okay. And this is basically what you have. So reverse mode will work, but it is not efficient because beta, the current gain, is very small. But not efficient. The BJT is designed and optimized to work with base emitter junction forward bias and base collector junction reverse bias. Okay, so that's how it is designed to be worked. So therefore, that is how you should use it, not the other way around. Okay, so that's about the active linear range, which is the most useful one in terms of amplification. Right? If you want to use it as an amplifier, this is how you should use it. Number 3 is the last mode, which we call the saturation mode. Saturation mode, in which case both base emitter and base collector junctions are forward biased. Okay, so they are both forward biased. So in which case, so VBE is greater than V forward of base emitter junction. VBC is also greater than VFBC. Now you will see that these values VBE and VBC, the forward voltages are not the same. For example, VBE, we said it's about 0.7 volts. This is about 0.5 volts. So therefore, what you will, if you look at the arrangement, what you have is something like this. The diodes. This is forward biased, and this is forward biased. Okay, so something like this. Okay, base collector emitter, something like that, right? So this is VBE, this is VBC. Now you will see that if this value is 0.7, this value is 0.5, what is this value? This is about 0.2 volts. So VBE, sorry, VCE, therefore, is about 0.2 volts. And can we use the external energy model here? What do you say? Can someone tell me whether we can use IC is equal to beta times IB? Is it valid here? Can someone answer? What do you think? We said in order for that to be valid, one junction has to be forward biased and the other one has to be reverse biased. But here both are forward biased. So therefore it doesn't work here. So beta is not equal to IC or IB. Okay, in fact, IC is much less than beta times IB. Okay, IC cannot increase as preferred, but IB can increase. Okay, so beta is much less. Beta is much less than 100 or whatever the value that you have. Okay, the IC divided by IB is much less than 100. Okay, now because there is no depletion layer, okay, remember there is no depletion layer because both are in saturation, both are forward biasing. There is no depletion layer. Right? Therefore, it is as if you have this whole thing connected from collector to emitter, because there is no, so everything is, there is no IC and IE has to be the same because the IB is very small, IB is small, but this whole thing can flow through IE. Okay, so basically IE is equal to IB plus IC, that is from Kirchhoff's current law. So anyways, and now IC becomes very close to IE anyway. Okay, so current IE is roughly equal to IC, and here determined by external circuit. That is the important thing. This value is determined by the external circuit. So if you look at the current, what will happen is base collector emitter. Now the current should, IB should go like that, and because both are forward biased, we expect this to go like this, right? But what happens is collector emitter, there is no depletion layer, so this also goes through that. Okay, this is what happens. So IBC is also flowing through this, IBE also goes through that. So they combine to flow through this. Hope this is clear. And this is, we'll when we talk about the when we look at the circuits, we'll say that we will show that this depends on the external circuit, not the it's not a property of the transistor itself. Okay, all right, is it clear? Everybody understand this? These are the three modes of operation for a transistor. Okay, now let's look at transistor characterization. We are going to move to a different section. How to characterize? How do you get the relationship between the inputs and outputs? Input in the input quantities and output quantities. Output quantities in the sense output current versus output voltage, input voltage versus input current, right? So that relationship. Now we call this transistor characteristics. Transistor characteristics. Now, what we are trying to achieve here is to obtain a relationship between for a transistor, output voltage is typically taken as the VCE, voltage between the collector and emitter. In output current is taken to be collector current, IC, right? So we want to see whether there is a relationship between IC and VCE. That's the objective of this exercise. So in order to figure that out, so you have the transistor. What we want is to see what is the relationship between the VCE and IC under different conditions. Okay, so this is the objective of this. So in order to do this, what we are going to do is we are going to change the current through the base IB. Okay, we want to change IB and also change the VCE, so applied voltages, and measure IC and VCE. Okay, so to do that, in order to control the base current, what I'm going to do is I'm going to connect a variable DC voltage source to the circuit, and I'm going to measure the current through it using an ammeter. But this current is very small, so therefore they are in the microampere range. So therefore, this is a microammeter. Okay, this is a microammeter. This is a fixed resistor RB, and I'm going to change this voltage. We call this VBB. I'm going to change it. So forget about the rest of the circuit. Look at this first. If I apply it like this, what will happen is, this is basically the VBB, right? As I change VBB, if you apply the Kirchhoff's voltage law, right? If you apply the Kirchhoff's voltage law, IB is equal to the current here. The current here is equal to VBB minus VBE. So this voltage minus this voltage, that's the voltage that is between this and that. So there is only RB here. So therefore, because the microammeter internal resistance is very small, so therefore this will be like that. You can express it like this. But we know when it is conducting, VBE is about 0.7 volts. It doesn't change. Okay, right. And then in order to, so now what we are going to do is we adjust this VBB and fix it. If you fix it, since VB is constant, B is constant, RB is constant, IB is not going to change. Okay, so we can set a value of value of IB by varying VBB alone, nothing else. And it doesn't depend on anything else, because RB is a constant value. When it is conducting, VBE is a constant value. Hope this is clear. And now what we are going to do is we are going to measure IC and VCE. Now to measure IC, we have to put an ammeter here to measure IA. So this is a milliammeter. And also we need to measure the voltage between emitter and the collector. So we put a voltmeter across this. The voltmeter to measure that. So this is going to measure IC, this is going to measure VCE. Right? Now, but now I want to change the current also here to measure to see what happens in this. Okay, so therefore I'm going to add a variable resistor here. I'm going to add not a variable resistor, a fixed resistor here, and a variable voltage VCC. Do you guys still hear me? I have a power cut, but still, do you guys hear me?
Yes, sir, we can.
Okay, so I don't know how long this is going to last, but we'll see. There is no power here. Hopefully the UPS will last for the internet connection. Okay? So we have this setup here. So under the situation where one of these terminals, one of these junctions, VBE is forward bias and BC is reverse bias. Under such situations, we can write that external energy model where IC over IB is equal to beta. So therefore, IC is equal to beta IB. Okay, this is only valid for external energy. This is only valid for one single situation. So let me write the value of IC by applying the Kirchhoff's voltage law here, right? Between this and that, this is RC, this is RC. So therefore, the current through this is the same as the current through that. So I can write IC is equal to VCC minus VCE, because this is 0. So this value is VC, which is equal to VCE, right? So therefore, this is basically nothing but writing the Kirchhoff's voltage law to the external circuit, where there is no voltage drop across the milliammeter. It is almost 0. Right? There is no resistance, almost 0 resistance. So this is equal to this divided by RC. So this is valid under any circumstances. VC we can change. VCE will change. Both VC and this are constants. In this case, this is constant and this is constant. This is constant only when this is forward bias, but under such situation. So therefore, this way I can control by varying VBB, I can control IB. By varying VC, by varying VCC, I can control VCE and IC. Now, when I change VCC, both VCE and IC will change, but I can measure both, right? By using this and that, I can measure both. So therefore, I have, I can actually find them, okay? Right, so what happens is, if I do this, by changing, so by changing VBB, we can set IB to a desired value, to different set of values, different values, right? So for example, I can set IB is equal to 0, or IB is equal to 10 microamperes and 20 microamperes, etc. Right? I can do whatever I want simply by changing VBB. Now, by the way, if I get disconnected, kindly give me someone, let me know by giving me a call. You have my number in the WhatsApp group, so you give me a call, okay? Not through WhatsApp, just physical call. Right. So for now, once I set the IB for each value of IB, okay, IB can be 0, IB can be 10 microamperes, whatever it is. Okay, now I have IB is equal to 10 microamperes. Now vary the VCC, the supply voltage, and then measure both VCE and IC, okay? And then plot it. If you do that, what you will see is that you will get a figure like this. VCE, you measure it. IC, you measure it, right? Now, under what conditions? You get, so you will get a graph, right? Yes. Okay. So let's say I have zero current. So obviously, if you have zero current, there is not going to be IC cutoff mode. So therefore, you will have something like this, almost 0. There is no current. There may be a leakage current. Remember, there is a leakage current. It is possible. So therefore, this value is IB equals to 0 microamperes. As you change the values, you will measure. So I change VC and IC. They will be something like that on this. So almost 0. Okay. So IB is equal to 0 microamperes. Now, if I change IB to some other value, it will, let's say 10 microamperes, it will initially increase. And again, it will come to something like that. Okay. So if I plot it, it would look something like this. So this IB equal to 10 microamperes. Similarly, you can change the IB value to 20 microamperes. You will see something like this. 30, like that. 40, like that. Okay. Like this, you can see they will vary like that. All right. So if you observe, now this is called the transistor characteristics. So these are for constant IB values. These are different curves for the relationship between IC and VC. This is called the transistor's output characteristics. Output characteristics. Okay. Now, why output characteristics? Because IC is the output current, and VCE, this is the output current. And this is the output voltage. So its output characteristics is a relationship between output voltage and output current. Okay. So this is basically IC versus VCE. So IC versus VCE, IC versus VCE is called the output characteristic. Right? Now note that if you have this, these areas where you have flat area, right? So note that IC is constant when IB is constant for some value. So this is when IB is constant, IC is also constant, right? So this is IC1. Let's say this value is 1 milliamperes. Let's call this 1 milliampere. This may be 2 milliamperes. This may be 3 milliamperes. This may be 4 milliamperes. Okay. So IC is equal to beta times IB under certain for certain set of values of VCE. Okay. This is called the active linear region. This is called the active linear region in active linear region. So this active linear region we can mark as this area. Okay, this is my active linear region, right? This area. This is called active linear region. And this area where you have no current, this area is called the cutoff region. There is no current in any of the branches there. And the area here, this is called the saturation region. in which current changes, but the voltage does not change. Output voltage VCE is almost constant, but current changes in this direction. Okay? So this is the saturation region. So this is what we call the transistor output characteristics. Okay? This is the transistor output characteristics. Okay? We can clearly see three regions here. Okay, but in addition, what happens if you have too much energy dissipation, like when the current as well as the voltage is high, for example in regions like here, right above here, when VCE times IC, that is the power, right? Power is equal to VCE times IC. If this power dissipation in this transistor is more than the amount of heat that can be taken away, then what will happen is heat will accumulate, and after a while it will come to a very high temperature and it will melt down the junctions. So therefore this is called the breakdown region. So anything above a certain value of VCE IC, so VC times IC is a constant, right? The power that can be dissipated. So that is called, so let's mark it somewhere outside this region. Let me use some color black. Okay, let's say something like this. It will go like that. Okay, so this area, it will melt down the thing. So therefore we call this the breakdown region. Yeah, P equals VCE IC is greater than P max. Greater than P max. Okay, so that's the that's when it all melts down. We can observe 4 regions of operation. One, cutoff region. In which IB is almost equal to 0, IC is almost equal to 0, or very small, only the leakage current. And output current does not change appreciably with the output voltage VCE. Okay, current IC does not change appreciably with output voltage VCE. Okay, both PC and BE junctions reverse bias. So power in this IC VCE, because IC is very small, right? So therefore this is almost 0. No power is dissipated. Okay, no power is dissipated. So nothing happens really. Second region is called the active linear region. active linear region in which IC does not change appreciably with VCE either, right? Even in this, IC does not change appreciably with VCE, output current. Okay, again. So, however, VCE is greater than 0. It is big. It's not small. It varies and it is greater than 0. And also IC is also greater than 0. Okay? Both are greater than 0. And in fact, IC can be written as theta IB because you have the external energy model applied here and which is greater than 0. So what can you say about the power? Both VC and IC are greater than 0. That should be greater than 0. It is a high power dissipation can be expected. And the lines are parallel. IC lines are parallel. Okay, these lines are parallel. These lines, this is parallel to this, parallel to this, parallel to this. These are parallel. Okay. The lines are parallel. Power VCE times IC is greater than 0 because both VCE and IC are greater than 0. Okay? So this dissipates a lot of power. So when you operate the transistor in this mode, it gets heated up. It gets heated up. If that heat cannot be taken away efficiently, it is going to go into breakdown region. If you put it in a enclosed space where you cannot dissipate the heat efficiently, it's going to burn. Okay, so that's something that you need to keep in mind. Number 3 is saturation. Where VCE does not change appreciably with current. Appreciably with IC. And IC is is not equal to beta times IB. In fact, IC is less than beta IB. Beta is a constant for the transistor. So it's less than that. In other words, current in the base can be higher than, they can be higher, but the current in the collector does not increase. It's fixed. Okay. Collector emitter voltage roughly is constant around 0.2 volts, which is very small, right? Which is for silicon transistors, we can assume this to be 0. So therefore, the power, which is equal to VCE times IC, but since this is roughly equal to 0, this is very small, very little power dissipation. Very little power dissipation. Okay. And number 4 is breakdown. I will just finish this and complete. Breakdown region. Large IC and large VCE. Okay, this is part of the active linear region activity. But when it goes into breakdown, it doesn't behave as the active linear region. This is large power. VCE times IC. Okay. Power dissipation approaches breakdown levels and does not behave as expected. and does not behave as expected in the IB times beta is not equal to IC. Okay. In fact, IC in this case is much bigger than beta IB. Okay, so that is why it goes into meltdown. Okay, all right. So let's stop this class here, and we'll continue from here the next day. But if you have any questions, you can ask now. Any questions from this section, what we have talked about? No questions? All right, so let's stop it here, and we'll meet on Monday. Now, actually, I only have a very small section on this transistor characteristics, that is on input characteristics, which is basically the same as diode characteristics, we'll see. And we'll talk about that as well as biasing in the next class. And from next class onwards, we'll have a physical class next week on Monday. After that, I will upload recorded lectures from previous year, basically, recorded lectures on different sections. And once every week, we'll meet and discuss these things, as well as we'll look at some additional problems. So we can spend some time on problem solving also because of this. Yeah, so I hope when I make the lectures available on fields, you to actually go through them and come to the discussion class, understanding them. And if you have any doubts, you can ask questions. Okay. All right. Let's stop the lecture at this point.